Something is wrong with the universe. Not wrong in the way a machine malfunctions. Not wrong in the way a calculation produces an unexpected number. Wrong in a deeper, more unsettling sense. Wrong in the way that suggests the rules you were taught, the framework you were given to understand existence, may not be a description of reality at all. They may be something far stranger. A story, a projection, a layer of interpretation stretched over something that refuses to be fully understood. You've probably never thought about this on a Tuesday morning. You wake up, the floor is solid beneath your feet, gravity holds you in place, light comes through the window at the speed it always has, and the world behaves exactly as expected. Everything confirms what you already believe, and that confirmation feels like truth. But here's what no one tells you at the start. The universe doesn't care what feels true to you. It has been running its own experiment long before you arrived, and the results of that experiment have been quietly accumulating for decades in laboratories, in telescopes pointed at the edge of the observable universe, in particle accelerators buried underground, in the careful, obsessive work of scientists who expected to find confirmation of the familiar, and instead found something that should not exist. What they found didn't arrive with a dramatic announcement. There was no single moment where someone stood up and declared that everything humanity understood about reality was now in question. Instead, it came in pieces, anomalies buried inside datasets, numbers that didn't align, measurements that repeated correctly but pointed to conclusions that made no sense, and then more of the same, and more, until the pieces formed a pattern that could no longer be dismissed, debated away, or blamed on instrument error. The pattern suggested something had been wrong all along. This video is about that pattern. It is about what was found, where it was found, and what it means not just for physics or cosmology or quantum mechanics, but for something far more intimate, for what you are, for what you are standing on, for whether the reality you perceive and the reality that actually exists are the same thing at all. Start with this question. Just let it sit in the back of your mind as you watch. The question is simple. What if the universe is not behaving the way it should? Not because we lack the tools to understand it, but because it was never meant to be understood by something like us? Hold that question, we'll come back to it. Before the cracks appeared, the picture looked almost perfect. For most of the 20th century, physics had achieved something extraordinary. It had built two towering frameworks, each describing the universe at a different scale, and each so precise that their predictions matched experimental results to a degree that borders on the incomprehensible. These weren't rough approximations. These were structures of logic, so refined that they correctly predicted the behavior of particles, fields, forces, and energy, with an accuracy sometimes exceeding 1 part in a billion. The first framework was Einstein's general theory of relativity. It described gravity not as a force in the traditional sense, but as a curvature of space-time itself. Mass warps the fabric of space and time around it, and other objects follow the curves that warping creates. This theory predicted black holes before anyone had detected them. It predicted gravitational waves, ripples in space-time caused by cataclysmic cosmic events, decades before the technology existed to measure them. When that technology finally arrived, it confirmed Einstein's calculations with stunning precision. The second framework was quantum mechanics, where relativity governed the vast and the massive. Quantum mechanics governed the infinitely small. It described how particles behave at the subatomic level, how energy is exchanged in discrete packets called quanta, how probability replaces certainty at the smallest scales. From this framework came semiconductors, lasers, MRI machines, and the entire digital infrastructure of modern civilization. Quantum mechanics is, by some measures, the most experimentally verified theory in the history of human knowledge. Together, these two frameworks seem to cover everything, the very large and the very small, the cosmic and the microscopic. You could look at any phenomenon in the universe and, in principle, place it within one framework or the other. The universe in this picture was a machine with knowable rules. Complicated, yes. Vast, certainly. But ultimately readable. Ultimately explicable. And then there was the standard model of particle physics, which cataloged the fundamental building blocks of matter and the forces that govern them. Quarks, leptons, bosons, the electromagnetic force, the strong nuclear force, the weak nuclear force. Each particle identified, each interaction described. When physicists at the Large Hadron Collider announced the discovery of the Higgs boson in 2012, it felt like the final puzzle piece clicking into place. The model was complete, or so the story went. You were handed this picture at school. Maybe not in these exact terms, but the underlying message was the same. Science had figured out the basic structure of the universe. There were still questions remaining, interesting ones, but the framework was solid. The foundation was trustworthy. You could build your understanding of reality on it and feel confident in that foundation. That confidence is precisely what makes what comes next so disorienting. Because the universe, it turns out, had not been consulted about any of this. The crack appeared in the data quietly, the way most profound discoveries do. It started with a number, or rather, with a disagreement between two numbers that should have been identical. Cosmologists have a value they call the Hubble constant, named after Edwin Hubble, the astronomer who first demonstrated that the universe is expanding. This constant describes the rate at which that expansion is happening. The higher the Hubble constant, the faster the universe is expanding. The lower, the slower. It is one of the most fundamental quantities in all of cosmology. If you want to understand the age of the universe, its future, its structure, its history, you need this number. For decades, scientists worked to measure it with increasing precision. And for a while, despite some disagreement in the details, the measurements were close enough to feel like progress. Different methods were converging. The community expected that as instruments improved, the remaining gaps would close. This is how science is supposed to work. Greater precision, tighter agreement, convergence on truth. That is not what happened. Instead, the gap widened, and it kept widening even as measurements became more precise, even as sources of error were systematically eliminated, even as completely independent teams using completely different methods arrived at their numbers through completely separate chains of reasoning. There are two primary ways to measure the Hubble constant. The first method looks backward. Scientists analyze the cosmic microwave background, the ancient glow of radiation left over from the Big Bang, essentially the oldest light in the universe. By studying the subtle patterns in that radiation, they can model the early universe and calculate what the expansion rate must have been. This calculation is anchored to the dawn of time itself. It gives a value for the Hubble constant of approximately 67 kilometers per second per megaparsec. The second method looks at the present. Scientists use a chain of distance measurements called the cosmic distance ladder, anchored by observable phenomena like Cepheid variable stars and type Ia supernovae, to directly measure how fast galaxies are currently moving away from us. This gives a value of approximately 73 kilometers per second per megaparsec. 67 versus 73. That might sound like a small difference. A rounding error, perhaps. A measurement inconsistency that will eventually resolve itself. It isn't. The gap between these two values is now measured at statistical significance levels that, in any other field of science, would be considered definitive proof that something is fundamentally wrong. The probability that this discrepancy is caused by random measurement error has been calculated at less than 1 in a million. Both teams have checked their instruments, their assumptions, their methods. Multiple independent groups have replicated both results. The numbers are not converging. They are holding firm on opposite sides of a gap that has no explanation within the current model of the universe. Scientists call this the Hubble tension. It is one of the most serious problems in modern cosmology. But calling it a tension feels almost too polite. What it actually represents is a fracture, a point where the universe is telling us in the most precise scientific language available that something is wrong with our understanding of it. And what makes it worse, what makes it genuinely unsettling rather than simply academically interesting is this. Both measurements are correct. Both methods are valid. Both are pulling the same number from the same universe, using different windows into the same reality, and arriving at answers that cannot both be true. Not if the universe we think we know actually exists the way we think it does. Something somewhere in that picture is broken. If it were only the Hubble tension, you might tell yourself it was a solvable problem, a missing variable, an overlooked effect. Something that a smarter equation or a better telescope would eventually explain. That is how science usually works. You find an anomaly, you investigate it, you update the model, and you move on. But the Hubble tension is not alone. Consider dark matter. In the 1970s, astronomer Vera Rubin was studying the rotation of galaxies. She was looking at how stars at the edges of galaxies orbited around the galactic center, expecting to find behavior consistent with what was observed in our own solar system. When objects orbit a central mass, those farther from the center orbit more slowly. It's the same pattern you see with the planets. Mercury moves fast, Neptune moves slow. The relationship is predictable and well understood. Rubin found something completely different. Stars at the outer edges of galaxies were moving just as fast as stars closer to the center. Not slower, the same speed. By all rights, given the amount of visible mass in those galaxies, those outer stars should have been flung outward into intergalactic space long ago. Something was holding them in place. Something with mass. Something with gravitational influence. Something that produced none of the light, radio waves, infrared, radiation, or any other form of electromagnetic signal that every known form of matter produces. Scientists called it dark matter, and the name is appropriate because what they were really acknowledging is not that they had discovered something, but that they had identified an absence. A gravitational effect without a visible cause. A force without a known source. By current estimates, dark matter makes up approximately 27% of the total mass energy content of the universe. 27%. More than 5 times all the matter you can see, touch, detect, or interact with in any direct way. Decades of searching have found nothing. Not a single confirmed dark matter particle. The experiments have grown more sensitive, more sophisticated, more comprehensive. The searches have extended into regions of possibility that would have seemed inconceivable a generation ago. And still, nothing. Whatever dark matter is, it refuses to be found by any method that has ever detected anything else. It follows none of the rules that everything else follows. It exists only as an inference, a placeholder for a mass that must be there because the universe doesn't add up without it. Think about what that means. More than a quarter of everything that exists in the universe is, from the perspective of every instrument and detection method available to modern science, completely invisible and completely undetectable. It influences everything. It shapes galaxies, steers cosmic structures, and holds the large-scale architecture of the universe together. But it cannot be seen, touched, measured, or identified. If that unsettles you, wait. Dark energy is worse. In 1998, 2 independent teams of astronomers were studying distant supernovae to measure the expansion rate of the universe. Both teams expected to find that the expansion was slowing down. This made perfect sense. The Big Bang had set the universe expanding outward, but gravity was supposed to be pulling everything back together. Over time, that gravitational attraction should be putting a brake on the expansion, decelerating it. The question being investigated wasn't whether the expansion was slowing, but by how much. Both teams found the opposite. The expansion of the universe was not slowing down. It was accelerating. Something was pushing galaxies apart at an increasing rate, overcoming gravity across the entire scale of the observable universe. Something was infusing empty space itself with a repulsive energy that grew stronger as the universe grew larger. They called it dark energy. And if dark matter represented 27% of the universe's total content, dark energy represented approximately 68%. Let that calculation complete itself in your mind. Visible, detectable, measurable matter and energy, everything you have ever seen or touched or that any instrument has ever recorded. accounts for approximately 5% of the total content of the universe. 5%. The remaining 95% is composed of two things that have never been directly detected, whose fundamental nature remains completely unknown, and that behave in ways that modern physics has no satisfying explanation for. You are living in a universe where 95% of everything that exists is, in the most literal scientific sense, a mystery. But here is where it gets stranger still. Because those anomalies, as profound as they are, exist at the scale of the cosmos. They concern things that are unimaginably large and unimaginably distant. You might reasonably tell yourself that they are problems for cosmologists to sort out, that they don't affect the world you actually inhabit, the world of solid floors and morning light and predictable cause and effect. The quantum world would like a word with you. You are made of atoms. Every part of you, every cell, every molecule, every signal that travels through your nervous system is built from atoms. And atoms are built from subatomic particles. And subatomic particles, as described by quantum mechanics, do not behave the way anything you have ever experienced behaves. They follow rules so different from the rules of everyday life that even the physicists who work with them professionally struggle to describe what is actually happening without retreating into purely mathematical language. Consider the double-slit experiment. It is, by many measures, the most important experiment in the history of physics. And it describes a behavior so bizarre that it has never been fully explained in over a century of trying. The setup is simple. You fire particles, one at a time, at a barrier with two narrow slits cut into it. Behind the barrier is a detection screen that records where each particle lands. If particles are simply tiny, solid objects, the pattern on the screen should show two distinct clusters, one behind each slit, reflecting the paths the particles took. Instead, you see an interference pattern. Alternating bands of high and low particle density, the kind of pattern you would get if you were sending waves through both slits simultaneously and allowing them to interfere with each other. The particles are behaving like waves, but they are particles, and you are firing them one at a time. There is no other particle for each particle to interfere with. The only way to produce the observed interference pattern is if each individual particle somehow passes through both slits at once, interferes with itself, and then arrives at the screen. This is not a metaphor. This is the measured, replicated, experimentally verified behavior of matter at the quantum scale. Now it gets more unsettling. If you place a detector at the slits to observe which slit each particle actually passes through, the interference pattern disappears. The particles suddenly behave like solid objects again, passing through one slit or the other, producing two clusters. The act of observation, of gaining information about the particle's path, changes the behavior of the particle. The interference pattern only appears when no one is looking. You can sit with that for a moment. The way a particle behaves depends on whether it is being observed. Physicists have spent a century debating what this means. The most widely accepted interpretation, called the Copenhagen interpretation, essentially says that before measurement, a particle exists in a superposition of states, all possible states simultaneously, and the act of measurement collapses that superposition into a single definite outcome. The wave function, the mathematical description of the particle's probability distribution, is not a description of ignorance. It is a description of reality. The particle doesn't have a definite position or trajectory until something interacts with it and forces a decision. Think about what this implies for the ground beneath your feet, the atoms in the air around you, the particles that make up every object in your field of view. At the fundamental level, none of them have definite properties until they are observed or interact with something. The entire physical universe, at its most basic level, is a field of probabilities that collapses into apparent reality only when something looks at it. What is looking? What counts as looking? These are not simple questions, and the answers that different interpretations of quantum mechanics provide are, in their own way, as unsettling as the questions themselves. The physicists who had built the quantum mechanical framework understood from very early on that something about it resisted intuitive explanation. Richard Feynman, one of the most brilliant physicists of the 20th century, said explicitly that nobody understands quantum mechanics, not in the way you understand how a bicycle works or how a bridge stays up. You can use quantum mechanics to make predictions of extraordinary accuracy. You can build technologies with it. But what it is actually, describing what is really happening inside the quantum world, remains genuinely contested. This is not a minor philosophical disagreement among academics. It is a foundational gap at the heart of the most successful theory in physics. The formalism works. The predictions are correct. But the interpretation, the question of what it means about the nature of reality, is unresolved. And depending on which interpretation you accept, the universe looks radically different. In the Copenhagen interpretation, the wave function is a calculational tool. It describes probabilities, not a physical reality that literally exists before measurement. When you observe a particle, you don't reveal what was already there. You cause something to come into being that was previously undefined. In Hugh Everett's many worlds interpretation, there is no collapse. Every possible outcome of every quantum event actually occurs, each in its own branching universe. The quantum wave function never collapses. It expands. Right now, in this moment, as you process this sentence, the universe you occupy is one of an astronomically vast number of branches, each one the result of every quantum event that has ever occurred, choosing every possible outcome simultaneously. You are not in the only universe. You are in one universe, and you can never reach the others. In the pilot wave theory, particles are real and do have definite positions at all times, but they are guided by a real wave that exists in a higher dimensional configuration space. The apparent randomness of quantum mechanics is not fundamental. It is a consequence of hidden variables we cannot access. The universe is deterministic, but its full state is partially hidden from us. These are not equivalent descriptions of the same thing. They are radically different pictures of what reality is. And the extraordinary troubling fact is that, at present, there is no experimental way to distinguish between them. All three give the same observable predictions. All three are consistent with every experiment ever performed. You cannot look at the data and decide which one is true, because the data does not decide. The universe has not given us the information needed to resolve the question. You are being asked to live in a reality whose fundamental nature is genuinely, verifiably unknown, and it goes further. Quantum mechanics and general relativity, the two great frameworks of modern physics, are incompatible, not slightly in tension. Genuinely, mathematically incompatible. When you try to apply the equations of quantum mechanics to the conditions described by general relativity, specifically to extremely high densities of matter and energy, like those inside black holes or at the moment of the Big Bang, the equations produce infinities. Not very large numbers. Actual infinities. Outputs that have no physical meaning. Physicists call this the problem of quantum gravity. It is the deepest unsolved problem in theoretical physics. String theory, loop quantum gravity, and a dozen other frameworks have been proposed as solutions. None have been experimentally confirmed. Some are arguably unfalsifiable by any technology that could ever exist. The universe has a known structure at large scales. It has a known structure at small scales. And where those two structures should meet, at the very foundation of reality, there is a hole. A place where our understanding breaks down completely, and our best equations produce nonsense. Here is where I need to step back for a moment, because something about this sequence of problems deserves to be held together all at once. You have a universe that is 95% undetectable and unexplained. You have an expansion rate that cannot be reconciled between two independent measurement methods. You have particles that exist in multiple states simultaneously until observed. You have the act of observation itself changing physical reality. You have two irreconcilable theories that each work perfectly within their own domain but cannot be unified. And you have, at the very center of the largest objects in the universe, a region called a singularity, where matter is compressed to infinite density, where space and time themselves cease to have meaning, and where every equation in modern physics fails. Each of these could be explained away in isolation. Any single anomaly is just an open question, a problem waiting for the right genius to solve. But when you hold all of them simultaneously, a different impression begins to form. Not that the universe is complicated and science needs more time, but that there is something systematically wrong with the picture. That the strangeness is not incidental. That the universe is not merely incompletely understood, but that it is strange in a way that may be irreducible. When I sit with this, really sit with it, what strikes me most is not any individual anomaly. It's the consistency of the strangeness. Every time physics pushes deeper, every time instruments become more sensitive and theories more refined, the mystery doesn't shrink. It grows. And it grows in a particular direction, always toward the same implication, that the universe as directly experienced and the universe as it actually exists may be fundamentally different things. Consider what observation does at the quantum scale. Reality, at its most basic level, appears to become definite only through interaction, only through the act of something engaging with something else. There is a word in physics for this process: decoherence. When a quantum system interacts with its environment, the superposition of states effectively dissolves into a single classical outcome. The quantum weirdness disappears and ordinary, solid, predictable reality emerges. But here's the thing. Decoherence doesn't solve the measurement problem. It describes the transition from quantum to classical in mathematical terms, but it doesn't explain why there is a specific outcome at all. Why this position and not that one? Why this world and not another? The appearance of solid classical reality emerging from a quantum substrate is, in a deep sense, still not understood. The floor you are standing on is not solid in the way it appears. It is a vast collection of particles that are, at any given moment, vibrating, interacting, existing in slightly probabilistic states, held together by quantum mechanical forces that themselves have no entirely satisfying classical description. The solidity is an emergent phenomenon, a large-scale pattern arising from underlying chaos, and the underlying chaos follows rules that we can describe but cannot fully interpret. Solid ground, it turns out, is a story that matter tells when there's enough of it in one place. There is a specific discovery made in recent years that deserves to be held at the center of this conversation, not because it is the most dramatic, but because it is the most precise. Because it involves a number, a single measurement, that should not exist within the framework of current physics. And it has been confirmed. In April 2021, the muon G2 experiment at Fermilab announced results that sent a quiet tremor through the physics community. A muon is a particle similar to an electron, but about 207 times heavier. Like an electron, it has a magnetic moment, a property that describes how it interacts with magnetic fields. Quantum mechanics predicts the exact value of this magnetic moment with extraordinary precision. The calculation incorporates every known particle and force in the standard model. It has been refined over decades to a precision of parts per trillion, making it one of the most accurate predictions in all of science. But when you actually measure the magnetic moment of a muon, the value you get does not match the prediction. The difference is small, astronomically small, but it is consistent, and it has now been measured with a statistical significance of 4.2 sigma, meaning the probability that it is a random fluctuation is roughly 1 in 40,000. When the Fermilab result was combined with previous measurements from Brookhaven National Laboratory, the combined significance approached 4.2 sigma, and further data collection has continued to solidify the discrepancy. The standard model is the most rigorously tested theory in physics. It accounts for every known particle and force. It has passed test after test for 50 years. And something is causing muons to behave differently than the standard model predicts. Something is affecting their magnetic properties that isn't in the model. Something exists, something that interacts with matter at the quantum level, that our current picture of the universe does not account for. This is not a theoretical anomaly or a philosophical puzzle. This is a hard experimental number that does not fit, a measurement that has been made and remade by different teams with different instruments and continues to produce the same deviation. The universe is doing something that our best description of the universe says it shouldn't do. The scientific community has a name for what might explain this. They call it new physics. New particles, new forces, new fields, something beyond the standard model that is subtly influencing these measurements. Several candidate theories exist. Supersymmetry, which predicts a whole family of undiscovered partner particles for every known particle. Dark photons, hypothetical carriers of dark sector forces, extra dimensions that only certain particles can feel. None of these have been confirmed. Each comes with its own set of unanswered questions, and each, in its own way, implies that the universe contains ingredients that are not in any current recipe. But here is what I want you to hold on to about this particular anomaly. Because unlike dark matter, which exists at galactic scales and cosmic distances, the muon anomaly is right here, in the machinery of the universe that builds matter, in the electromagnetic properties of particles that compose your body, the air around you, the screen in front of you. The discrepancy is happening at the most intimate level of physical reality. Whatever is missing from our equations is not out there at the edge of the observable universe. It is here, embedded in the fabric of the matter you are made of. Now let's go somewhere even less comfortable. Time. You experience time as a flow, a river that moves in one direction from past to future, carrying you along with it. The past is fixed, inaccessible, immutable. The future is open. Causality moves in one direction. You remember yesterday. You cannot remember tomorrow. This asymmetry is so fundamental to conscious experience that it feels less like a property of the universe and more like a property of existence itself. Physics does not agree with your experience. At the level of fundamental physical laws, time is symmetric. The equations that describe the behavior of particles, whether quantum mechanical or classical, work equally well in both directions. If you filmed a collision between two particles and played the film backward, the reversed collision would be just as physically valid as the forward one. The laws of physics do not prefer the future over the past. Both directions are equally allowed. There is only one law in physics that distinguishes the past from the future, and it is the second law of thermodynamics. Entropy increases. Systems tend toward disorder. A broken egg does not reassemble. Smoke does not flow back into a cigarette. The arrow of time you experience is, according to physics, a statistical effect. It emerges from the fact that there are vastly more disordered states than ordered ones, so systems naturally evolve toward disorder over time. The direction of time is not written into the fundamental laws of physics. It is a consequence of statistics. But that explanation, while technically coherent, does not resolve the unease it should produce, because it means that the rigid, one-directional flow of time you experience as the container of your life is not a fundamental feature of the universe. It is an emergent phenomenon, something that arises at large scales from underlying laws that don't actually require it. The physics works just as well in reverse. The directionality is something the universe seems to impose only at the scale where you can perceive it. And then there's quantum mechanics again, adding another layer. In quantum mechanics, certain rare processes violate what is called time reversal symmetry. They have a preferred direction in time. The kaon and the b meson have been observed decaying in ways that are not perfectly symmetric in time. This is called CP violation, and its existence is one of the reasons matter survived the Big Bang instead of annihilating with antimatter. The universe at the quantum level has a subtle but real preference for certain directions in time under certain conditions. What this means, taken together, is that time is not what it appears to be. The rigid, universal clock you imagine ticking at the same rate everywhere is already gone, dismantled by special relativity, which showed that time passes at different rates depending on your velocity and gravitational environment. GPS satellites have to account for time dilation because time runs measurably faster in orbit than at Earth's surface. Clocks taken on high-speed aircraft and returned to Earth are measurably behind the ones left on the ground. Time is not fixed. Time is not universal. Time is not even clearly defined at the quantum scale, where several theoretical frameworks suggest it may not be a fundamental ingredient of reality at all, but an emergent property, something that arises from the correlations between quantum systems rather than something that exists as a background against which events occur. If time is not fundamental, what does that mean for your experience of existing? For memory? For the sensation of moments passing? For the feeling, which seems more certain than almost anything else, that there is a before and an after, that you are moving through time in a specific direction, that the past is gone and the future is coming? Physics says that feeling is real. But what it is describing about the universe may be something far stranger than the river you imagine. There is a place in the universe where everything that has been described so far reaches its absolute extreme. A place where space-time bends to its breaking point, where matter reaches infinite density, where the laws of physics fail entirely to describe what is happening. You already know its name: a black hole. Black holes are not science fiction. They are not theoretical constructs. They are among the most confirmed objects in modern astrophysics. In 2019, the Event Horizon Telescope released the first image of a black hole, the supermassive black hole at the center of galaxy M87, 55 million light-years from Earth. The image matched predictions from general relativity with remarkable precision. In 2022, the collaboration released an image of Sagittarius A, the supermassive black hole at the center of our own galaxy, approximately 26,000 light-years from Earth. At the center of a black hole is a singularity, a point of infinite density. This is not a poetic description. It is the mathematical output of general relativity's equations when applied to the collapse of a sufficient mass. The equations don't just produce a very large number at the center, they produce an infinite one, and an infinite density has no physical meaning. It is a signal that the theory has broken down, that the equations are no longer describing reality because the situation they are being asked to describe exceeds the domain where their description is valid. This is troubling enough. But in 1974, Stephen Hawking made a discovery that turned the black hole problem into something far deeper and far stranger. By combining quantum mechanics with general relativity, Hawking showed that black holes are not actually black. They emit radiation, now called Hawking radiation, as a consequence of quantum effects near the event horizon. And this radiation causes the black hole to slowly lose mass and, over extraordinarily long timescales, evaporate entirely. The problem is what happens to the information that fell into the black hole. Quantum mechanics has a principle called unitarity. It states that information is never destroyed. The quantum state of a system may evolve in complex ways, but the total information contained in that system is conserved. This is not a philosophical preference. It is a mathematical requirement of the theory. If information were destroyed, quantum mechanics would break, and with it, the predictability and consistency of physics at the fundamental level. But if a black hole evaporates, what happens to the information about everything that fell into it? Hawking radiation is thermal radiation, essentially random noise. It doesn't carry the information encoded in the matter that collapsed to form the black hole. When the black hole is gone, that information appears to be gone too. This is the black hole information paradox, and it is genuinely paradoxical because both things that are producing the paradox, quantum unitarity and Hawking radiation, are derived from sound physics. Each is correct within its own framework, but they cannot both be right in the same universe. Something must give. Something at the foundation of physics must be wrong or incomplete. Hawking himself changed his position on this multiple times over his career. The physics community remains divided. Proposed solutions include the idea that information is encoded in the Hawking radiation in a subtle, scrambled way, that makes it recoverable in principle. Some proposals suggest that information is preserved in Planck-scale remnants left behind when the black hole evaporates. Others, more radical, suggest that the very geometry of space-time itself plays a role in encoding and preserving information in ways that current theory cannot yet describe. One of the most striking proposals is the holographic principle. This idea, which emerged from string theory and has grown into one of the most actively researched concepts in theoretical physics, suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. Like a hologram, where a three-dimensional image is encoded on a two-dimensional surface, the three-dimensional universe you inhabit might be a kind of projection of information stored on a two-dimensional surface at the cosmic horizon. If that sounds familiar, it should. It is a scientific framework that is structurally identical to the idea that the universe is a simulation, where all the information needed to generate a three-dimensional experience is stored and processed somewhere else, and what you perceive as the output. The simulation hypothesis. You've probably heard of it. You may have dismissed it as philosophy or science fiction, but it is worth spending time here, not because it is proven, not because it is even the most likely explanation for the anomalies being discussed, but because it is now taken seriously by physicists and philosophers precisely because those anomalies make it difficult to dismiss. The argument, in its most careful form, runs like this. If a technologically advanced civilization can create a simulation of conscious beings with a simulated universe, then given enough time and enough civilizations, the number of simulated realities would eventually vastly outnumber the number of base realities, which means that, purely statistically, it is far more likely that you are in a simulated reality than in the one original base reality. This is the simulation argument formalized by philosopher Nick Bostrom in 2003. It is not a claim that we are,